Hi, I'm Mithil Guru, a master's student at the University of Chicago, and today I'm talking about the work I did in collaboration with Romain, Nith, and my advisor Pedro Lopes. The topic of my talk is how we might envision a future of computing devices that assist us with physical skill acquisition. Specifically, I'm interested in systems for fine force adjustments. Let's see one. Say you're making your morning espresso. You prepare the coffee grounds, then place the portafilter in the machine and pull your shot. It's sour. You under-tamp the grounds, meaning you use too little force when pushing down on the coffee grounds. But you can't just press too hard either. Over-tamping also affects taste. This is a striking example of a simple movement, but with a complex force profile that you need to master before you learn to perform it regularly. It's hard to comprehend with just words. Like if I say strong, but not too strong, is not helpful without feeling it in your body. You can't learn about using force from a book. Learning a new physical skill requires repeatedly practicing movements. Today, even in an age of advanced interactive tutorials, many even powered by AI assistants, we still learn by watching and copying movements. This allows us to rapidly learn the trajectory of a movement, but what about force? How can you learn to tamp at the exact force for a perfect espresso? In recent years, HCI research has increasingly turned to interactive electrical muscle stimulation. This is sending small electrical impulses to the muscle to move users' bodies involuntarily. This technique promises a world where we can literally download interactive assistance to our body, so you can directly perform a skill. Recent HCI work has overwhelmingly highlighted the potential of EMS in demonstrating physical movements, with applications in learning instruments, playing sports, and even tool use. Yet, of the 150 plus papers discussing EMS and HCI, as according to this work right here, they almost exclusively focus on trajectories. Few examine the force component of the movement. Which leads to the question, can we accurately perceive a force if it's involuntarily demonstrated by EMS actuation? You'd expect with 150 plus papers in HCI alone, we'd have a very good grasp of this question, yet we don't. Some works have touched on forces, but they all miss the critical question. When EMS stimulates our muscles to produce a force, do we perceive exactly that force? Can we recall exactly that force? If you've never tried EMS or read into the neuroscience of it, you might be thinking, why should we expect it to be hard to replicate a force felt with EMS? Well, we do have strong reasons to ask this question. A well-documented limitation of EMS is the rapid force buildup of EMS-induced movements. When we move, our nervous system chooses what type of muscle fibers to move. However, with muscle stimulation, the contraction is involuntarily, so it leads to an unnatural recruitment of muscle fibers firing, resulting in a rapid force buildup. So we explore this in a user study. Can users accurately replicate force demonstrated by EMS? Let's have people grip at an exact force by EMS, then measure the difference between the force demonstrated by EMS and then the user's own recall. We tested this for 10 baseline trials across 3 force levels, minimum, midpoint, and maximum of their EMS-demonstrated grip force range, and randomized this across the set. When we observed results, recall forces were significantly higher than demonstrated forces. The median relative recall error was 19% higher than the demonstrated recall, suggesting participants tend to overshoot that force, recalling a much higher force than demonstrated by EMS. Here's an example force time visual of a participant who overshoots recalls. Demonstrations are in gray, recall trials are in orange, and the median is bolded. We can see that the error is proportionately greater for the lowest forces. So the effects we talk about, like EMS's rapid force buildup from fast fiber stimulation, does creep in. Naturally, as interface engineers, we were curious if we could model the user's perception of these forces so that we can compensate for the offset and allow them to feel the right force. In other words, going back to our study design, can we give users an adjusted reference force if we understand their perceptual model? Here's 3 simple perceptual models of the same participants' data from before, based on their demonstrated force to recall force scatter. We select the best fit model for each users. So here you can see all participant selected models evaluated with root mean squared error. The best fit model that was selected was highlighted in blue. After this, we invite users to try the same study again, but now comparing new unseen baseline forces and their paired model-adjusted forces in one merged set of trials presented in a randomized order. Do we see force recall improve with model-adjusted EMS? Yes. Model-adjusted EMS significantly reduced recall error when compared to baseline demonstrations. And when we look at the data across individuals' force ranges, we see the most improvement in the lower and mid force ranges, indicating that our model approach improved recall where offset was greatest. Now that we see that adjusting EMS to a user's perceptual model can improve their recall, we can add forces to this list moving forward, as force is inherently something EMS systems can depict as opposed to viewing a movement or reading it from a book. So what can this enable? Let me speculate for a moment. Standard EMS-demonstrated forces are shown to be perceived incorrectly. So by using model-adjusted demonstration, a participant can quickly learn the exact force to play a correct bar chord on guitar. Likewise, chiseling wood requires precise force application for paring cuts. And golf putting requires a consistent force application throughout the swing. By constructing a user's perceptual model in advance, we improve the EMS system's ability to convey precise force. Now, let's review what we found and what's next. Primarily, we found that users tend to overestimate force from EMS. However, we can improve significantly by modeling their perception of force. Despite this, recall isn't perfect. So how can we further improve EMS systems? Our first and foremost recommendation is to design EMS systems with multiple modalities such as audio and visual if available. However, when you are limited to a system with solely EMS, consider modeling user force recall like we did. The more stringent a force requirement is, the greater the perceptual offset or variability, improving the potential for improvement from our model. We envision future work to explore more force training domains, optimizing for precision of the perceptual model or optimizing for retention of target forces across more complex situations and muscle groups, paving way for more accurate force-focused EMS systems for physical skill acquisition. And hopefully this means better morning espresso for everyone. Thank you.